It's a pleasure to have Jure Zupan from University of Cincinnati. Jure is originally from a beautiful small country in Europe, Slovenia, and he graduated, did the Bachelor of Science, Master, and graduated with a PhD in 2002, and then has gotten various postdoctoral positions as usual. So first at Technion in Israel, then Carnegie Mellon, then back in Ljubljana, fellow at CERN, right. And then faculty in Ljubljana, and then University of Cincinnati, became assistant professor in 2007, and since last year is a full professor over there. And will give a talk kind of complementary to the one of last week, because I will speak about precision measurements in energy physics in another sense, not necessarily just the Large Hadron Collider.
All right, well, thank you very much for both the opportunity to give this talk and the nice introduction. So what I'll talk about is, so it will be particle physics. And when you are a physicist, then you go to a coffee shop and you talk to different people there, you chat. They find out you're a physicist, they want to know what you do. So what kind of a physicist? And I say a particle physicist. And they say, what does this mean? And I say, what exactly do you want? What exactly are you doing? And I would say, oh, it's very easy. No, we're searching for the Lagrangian of nature. So this is the goal of particle physics, is to know what is on the right-hand side. And the status of where we are is the following. So we know a lot already. So we know the standard model. So I think since I'm a particle physicist, I'm obliged to show this this figure with quarks and the gauge bosons, or the more modern version, which comes from the particle fever movie. So the Higgs boson, the gauge bosons, and the quarks and the leptons. However, we also know that the picture is not complete. So not everything is described by the standard model of particle physics. So there's dark matter. We don't know whether we cannot really explain the dominance of matter versus antimatter that we see around us, how we incorporate gravity into this quantum picture. And so I'll start with this, the following problem that we're facing. So there are two important scares here that I will focus on. The first one is there are strong interactions. So the interactions that bind quarks into nucleons and nuclei. The scale here is 1 GeV, so that's the energy scale. E equals mc squared, so the energy is also mass, so this would be 1 proton mass. And this is experimentally well explored. The other one is the weak scale, so it's the weak interactions. The scale is 100 GeV, so 100 proton masses, or if you want in terms of the distances, 100 times smaller distances. This is what is being explored directly at the Large Hadron Collider. And the issue here that I'll spend a few slides on is that this scale of 100 GeV is something which is unstable under radiative corrections, under quantum corrections. And it's kind of it's a mystery that it can be as low as only 100 proton masses. So this is called the hierarchy problem. And I will spend a few slides talking about it through an analogy. So the analogy is the following. So let's say that you have two companies, all right? And the only thing I know about these two companies is that their revenue is within $10 of each other. So I have a company A and a company B. They are earning money, and the difference between this revenue is $10. So the question that you can ask is, how big are the companies? Well, okay, so how big are they? Well, one good hypothesis is that these are two lemon stands that the kids have in front of their houses. They earn some money, and these guys are maybe a bit more successful and earn $10 more. All right? And then somebody tells you that, no, it's not the kids selling lemonade. It's the two of the largest companies in the US. So it's ExxonMobil and Apple. and each of them has a revenue of 200 billion. And then you say immediately, okay, this is very fishy. So first of all, it's impossible. They're doing different things. How can they have a revenue which is exactly cancelled to 10 digits? So there's somebody is cooking the books. There's a mafia at play. All right, so that's the hierarchy problem, no? Looks fishy. Now, it's actually much, much worse when you talk about the hierarchy problem in particle physics because it looks like this. All right, so that's the electroweak scale. So these numbers here are in GeVs. There's the QCD scales. These are the particles, the elementary particles that are measured. And the mass of this guy, the Higgs boson, is unstable under the quantum corrections. And you see that there are scales above, which would be, let's say, grand unified theory scale or the Planck mass. This would be where the quantum gravity so gravity would become quantized. Is much, much higher. No? It's 10 to the 18, where this is 10 to the 2 or 10 to the 13. So there's many decades difference between these different scales, and the Higgs mass should be pushed up to this very high value. So how is it possible that this is not the case? Is one of the fundamental problems of particle physics. And a common idea of how you solve this is through symmetries. So you would introduce a larger framework, for instance. So these are maybe just pictures, but this would be a quantum corrections that come from standard model, from Higgs coupling to top quark. And then you have an extra degrees of freedom that would cancel these contributions. So the way you can picture it is I have a standard model force that is balancing an iron ball on a tip of a nail. I want to balance it. I need two forces that balance each other to a very, very good approximation. And this is because there's a symmetry. You know? Of course, it's not accidental. It would be a symmetry. If you translate this into a particle physics language, we would expect, if this is the solution to the hierarchy problem, we would expect that there are many particles that will occur, I don't know, at 1 TeV. TeV here is tera electron volts. It's 1,000 times more than the GeV. So let's say thereabouts at the scales that we're probing. All right. So that's the hierarchy problem and an idea as to how it is solved in particle physics. All right. So how do we experimentally test this? So there are different probes that are being used. So it's a huge program, of course. The direct probe is through high energy collisions. You will just produce these new particles, or you hope you will produce them. There's the Large Hadron Collider at Geneva, Switzerland, which you heard about here last week. What I will focus on is a different frontier. It will be precision measurements. So the names that will appear are the experiment Bell 2, LHCb. I will say nothing about the other experiments. And then you can also, of course, you gain also information on particle physics indirectly through cosmology and astroparticle physics. So let me focus on this one set of measurements. All right, so here I think it's a good point that I just open a bracket and I will talk about something different, which is why is the weak force weak? All right, so let's address this question. So the background is the following. So if you look under the hood as to how the weak force, so the weak force is the one that is responsible for neutron decay to a proton and the electron and antineutrino. And the strong force, which binds quarks and gluons into nuclei. They're very similar if you look under the hood. No? They're both non-abelian engaged theories, so they are somehow look very, very similar when you write down the Lagrangian, no? The Lagrangian of nature. So therefore, why is the weak force so weak? Right? So the answer is that there are two parameters that are changing between the weak and the strong interactions. What you can change is the strength of the interaction itself. So it will be a dimensional numbers that will tell you how strongly you couple to these force carriers. But there's also the mass of the force carriers that changes. All right, so the weak force is not weak because the couplings would be small. It is weak because the force carriers are heavy. So let's look at this neutron decay to a proton, electron, and a neutrino. So what happens is, so this is mediated by a force carrier, a W boson. So the W boson will change a neutron to a proton, and then it will emit an electron and a neutrino. So this would happen. However, the way this happens is in a very peculiar way. W is much, much heavier than the neutron. It's 100 times heavier. So you cannot really produce a W boson. However, you can count on the uncertainty principle. I can create a W for a small moment of time. I cheat the energy conservation, but I can only cheat it for a small amount of time. And there's a price to pay for this. No? So the smaller the amount of time, the bigger this price I will pay. And the way you will see this is that the heavier this force carrier will be, the more suppressed this interaction will be. Okay, so this is more an analogy. It's not the real thing that is happening, but it gives you a feel for why this is going on. The problem why it doesn't really work is that even if I take an h bar to 0, this picture still is correct. H bar to 0, now you know that there should be no uncertainty principle. So I cheated a little bit, but I warned you also, so I'm not a complete cheat. All right, roughly you know, no? So the heavier the thing that I need to create for a small amount of time, the more suppressed this will be. And the suppression is this a factor of 100, so 100 times the proton mass, which is the weak scale that I'm talking about. All right, so now I'm ready to close the bracket. So why did I need this? Is because now we can use this to understand that, so as a good physicist, I can turn now this around. So a heavy guy means rare processes, which means that if I start looking at the rare processes, I will be able to probe scales which are much, much higher than what I'm able to produce, right? So rare process means heavy mediators. Instead of a W, if there's something which is much, much heavier, if I'm able to very precisely measure these transitions, I would be able to sense whether there is this new force carrier. So there's the recipe. If I want to indirectly search for new physics, I want to first identify the process which is rare in the standard model. That's the stuff that maybe I don't care about. And then search a deviation from these predictions. All right, so that's the recipes. That's the whole framework. So probably the most celebrated example, or the most useful one, are the so-called flavor-changing neutral currents. So what are these? So these are the following. So the following statement is true. So if I take a big quark, change it into a strange quark. So big quark has a charge of -1/3. Strange quark has a charge of -1/3. So that's the neutral in this acronym FCNC. The flavor is changing from B to S. So that's the flavor changing. And the current is just what we call this B to S transition. So this B to S, you cannot do with a photon exchange or a gluon exchange or a Z boson at this 3 level, which means in the H bar to 0 limit, or the Higgs exchange in the H bar to 0 limit. So it does not happen in the standard model. So it's good, no? It's the first step in our recipe. So identify transitions which either completely vanish or are suppressed by H bar. They do happen, for instance, at this really one loop correction, so the H bar non-zero. So there's the diagram like this. So I can take a B, convert it into a top and a W boson. And this will be there only if the H bar is non-zero. So it's really a quantum mechanical effect. However, it's suppressed, no? It's suppressed because I do pay a price of this h bar. Now I can measure these transitions and look for deviations. So deviations could come, for instance, from these heavier mediators. Let's call them X, Y. There can be different ways that you can change the transition. The important thing is that it will scale as 1 over the mass of this guy. So 1 over the mass squared of the new mediator. So the heavier the mediator, the more suppressed the probability is for this transition. The probability will go as a square of this Wilson coefficient. And it's also proportional to the coupling. So there's also dimensionless couplings, which sit in the numerator. So the bigger this coupling, the more probable it is. So the smaller the coupling, this will also disappear to 0. Right. So it depends on both couplings and the masses. I said there were 2 parameters which are the important in this business. All right. So this whole thing is, the program looks like this. No? So I am searching for some deviation somewhere. So like I go whale watching. I'm looking for whales. I see a tail, and as soon as I see a tail, I will be able to tell what kind of a whale it is. Now, if it's a blue whale, there will be a huge tail there. It's actually even better because these precision measurements are not just a measurement at the sea, but it looks more like a jungle. So there are many processes. You measure many processes. So even if you have a beast which is something like this, that it has a very small tail, if you're able to measure from different angles, we'll be able to figure out what's going on, right? So it's pretty good, no? So I'll show another celebrated example as to how this works with the check of the CKM unitarity. So the CKM is a matrix which sits, it parameterizes the strength of transitions that we were looking at already. So let's say I take one quark, and then it goes to a different quark. But here, there's a charge difference. So this B quark is charge minus 1/3. Up quark is a charge plus 2/3. And you have to emit a W boson, which has a charge of a minus. So this is flavor changing transition, but also charge changing. So it's a charge current. And there's a coupling here which depends on the flavor. This would be, sits in the CKM matrix. It's a 3 by 3 matrix because we have 3 down quarks, 3 up quarks. And the sizes of the elements are roughly denoted by the sizes of these dots that I put there. So it's mostly diagonal, and there are also these off-diagonal pieces. So what you can notice is that if there's a big guy in this column, there's a small guy in the third column. So if I take now a product of, let's say, the first times the third column, and use the fact that this CK matrix needs to be unitary in the standard model, we'll find a nice sum rule, which is that this column times that column complex conjugated gives me a 0. I can now denote this geometrically. So these are 3 sides of a triangle in a complex plane. Now these are complex numbers. And conventionally, what you do is you take this product and you divide by so you divide by this product so that this would be this side here. It's just 1 because I normalized it. And then this left and the right sides of the triangle are these ratios now. Right. Why this was done, okay, I don't know. But this is before my time. Also, of course, there are 2 conventions for what you call these angles. The alpha, beta, gamma is the US. The phi 1, phi 2, phi 3 is the Japanese way of denoting this. There were 2 experiments, Bell and Babar. And at the end, when the physics of these B factories was written up, there was a very famous coin toss which decided which of these two notations was used in the common physics of B-factories book, and the Japanese one. All right, so it's phi 1, phi 2, phi 3 is the official name. Anyway, so what I will show is exactly this triangle. You measure the sides. The apex is called rho bar, eta bar, again, just to confuse people that are not used to the jargon. But it's nothing scary, so you just measure these sides through different processes. And you want to see whether this triangle closes. So this was done at the B factories. So Bell and Babar were the two experiments that ran in the 2000s. They had about a billion B mesons each. There's also a new super, I'll call them both super B factories. LHCb has been running for 8 years already. It's at LHC, so Large Hadron Collider, B for B quark or B physics. And it will run for another 10 or maybe 15, 15 years. And they will have up to maybe 10 to the 11 Bs. Bell 2 just switched on, and they're also counting on about 10 to the 11 B mesons. So what you can see now is that there's a huge deflation going on in B physics. If you looked at how much one B meson cost to produce when you had to pay for the electricity and the fact that you're running B factories, it was about 2 quarters per B meson. And now, 15 years later, we're much more efficient, and the price dropped to 1 cent or below 1 cent per B meson. All right, so it's good, no? 50 times more statistics for the same amount of money. The progression looked like this. So that's the triangle. Maybe it's hard to see. These are the rho bar, eta bar. So that's the apex here, is this rho bar, eta bar. And then there are different measurements, are these blobs of color. So this was before B factories. And then as soon as the B factories switched on, first of all, you see there are many more measurements. And the common area is shrinking. So all these measurements, so let's say 2009, it shrinks even further. And there are more measurements appearing. And in 2016, it's even more reduced. So what does this teach us? It teaches us that everything looks standard model-like in this test. And that we're measuring more things. So let me go through what goes into here. For instance, just that you have an impression. So this would be, this band here is KK bar mixing, which is I take a meson which has an S quark and an anti-D quark, and it transitions into the D anti-S. So S goes to D, anti-D becomes an anti-S. Then there's a similar one. This yellowish band is B D bar to D B bar. Right? So B quark, anti-D quark, D quark, anti-B quark. The same thing, but I just replaced the D quark with an S quark. So that's this orange band here. There's the 3-level transition B to U, VUB, this CKM matrix element. So that's this green band here. And for instance, there's also this a more complicated one where I have a decay into states where I have 4 valence quarks. All right? So I think the only thing you want to really get out of this is that there are different choices for flavors of the quarks that were used, and the fact that all of them point to the same region is quite non-trivial, because it's an over-constrained system now. There are more measurements than there are parameters, so it's non-trivial that they all meet at this one point. All right? Okay, so another way of showing this is by converting all the measurements of this type into the bounds on the scale of new physics that you can still have. Right? So I said the mediators of new physics have to be heavy in order to not to see them. So what's plotted here, okay, this is is a particular transition, different flavors of quarks. So these are the CK, would be with the strain, CD, CBD, CBS. And then there are different choices for what kind of a mediator I can stick in. So the details are not really important. What is important is that even in the last decade, so after the B factory switched off, there was still a huge progress. So this is a logarithmic scale, no? So it's a logarithmic scale, TeVs, it's 1,000 proton masses. This is 10 to the 2, 10 to the 3, 10 to the 4. So first of all, these are huge numbers, no? You probe very high scales, very short distances. But also on the logarithmic scale, I can see the advancement. These are these white arrows, right? So why is this the case? It's because the analyses were completed. LHCb has made measurements. The people were able to do numerical simulations much better. So there was really a sort of, I would say, really an underappreciated. I definitely didn't appreciate it as much because it's, it's like it's a very slow progression from year to year. But if you go back and you look at where we were at 10 years ago, it's really a non-negligible jump. All right. All right. So now I painted the rosy picture of everything works. So now we come to the anomalies. So I would say like a one-slide summary of where this field is this one. So there are many different transitions measured. I talked about the subset. I showed some of these consistencies in the picture. But there are also some anomalies which seem to hint at new phenomena. And they are of two types. So they are of the following type, where you take a B quark goes to a C quark, a tau lepton, so that's the heaviest charged lepton, so doesn't carry strong interaction, and then the corresponding neutrino. This in the standard model is mediated by this W boson, but there's a hint of inconsistency there. And the scale of the mediator, so there's this scale that sits in front of the corresponding operator, is about 3 TeV, so 3,000 proton masses. The other set of measurements which somehow sticks out is the following. So you take a B quark, goes to a strange quark, and a pair of muon leptons, so mu plus, mu minus. So muons are the second heaviest, so it's an electron, muon, tau are the 3 charged leptons. In the standard model, you can only have this kind of a decay through quantum corrections. So in h bar to 0, this will disappear. So it's quite suppressed. And the new physics scale that could explain the anomaly will be 30 TeV or thereabouts. So 30,000 proton masses. All right? So now what I'll do is I'll spend some time going through one, so the left and the right-hand side, so the two transitions. So I'll start with this B to S mu mu, so B quark to an S quark and a muon pair. The upshot of what I will show you is that these are really theoretically very clean observables. So the measurements have almost no theory error. So all the potential problems could be in the experiment. And of course, that's why they spend so much time making sure that they're not making a mistake. Now, the other question is, well, does it make sense from new physics perspective? And I will not really tell you much. I will have really a far view of what you can do. But the message is that you can have a reasonable scale for new physics models, so the models that will explain this. But there is an asterisk there, which is that nobody really ordered this. It doesn't explain anything except for these anomalies, right? Which is, first, the Rabi's muon question. When muon was discovered, Rabi said, who ordered that? So I think this would be appropriate sentiment also here. All right, so the experimental situation. So now there will be not really questions, but a little bit more of physics information here. So I hope I don't lose you completely. But I need some more notation. So in the standard model, these are the diagrams that will mediate the transition. So we're looking at B quark to S quark plus 2 charged leptons. They are described by the following operators. So I have a B quark goes to an S quark and a charged leptons. And the L here tells me there is a particular type of a current. It will be a vector minus an axial vector current. And the gamma mu and the gamma 5 here are either a vector or an axial vector current on the lepton side. So the C9 coefficient will tell me the strength in the case where I have a vector current, so gamma mu here. C10 will tell me the strength when I have an axial vector current. Right? These are dimensionless quantities, and the way this was achieved is by this prefactor here. There's a Fermi constant and some just conventional normalization. Right? So the thing to remember is there are two dimensionless numbers that will tell me the deviation. This will be all parameterized by two dimensionless numbers. So there will be a few plots where I will show I will transform the measurements into the deviations in these Wilson coefficients. All right, so the measurements are the following. So there are so there are basically three numbers, three measurements. They're always in the ratios of transition where you have muon pair and the electron pair. That's useful because many errors in the theoretic prediction will cancel, and many experimental errors will also cancel, but not all of them, depending on what exactly you're measuring. These B and K are just some mesons. B meson has a B quark-in, K meson has a strange quark-in, so this is really B to S and a lepton pair transition. And the only thing I'm changing is the flavor of the lepton. There's nothing funny going on the quark side. This 1 to 6 bin refers to the invariant mass of the lepton pair. So the leptons could be closer together. This number would be smaller. If they make a wider angle, this Q squared is bigger. And this was measured in 2 bins. It was measured in 1 bin in this case. So this is the previous measured by LHCb. So this is one of these collaborations. These big error bars, and the small one is the one that you want to look at. Okay, maybe it's hard to see, but it's this black error bar with the smallest error bars, and the prediction is 1. So in the standard model, there is no difference between the coupling to muons and the electrons. We say that it's flavor universal. So this is 1 up to a percent, where this percent is probably even smaller. Then you look at the slightly different transition, which I'll have on the next slide, which the only thing I do is I take a different meson. There's a star there. It's a different meson. It still has a strange quark. And you probe a slightly different structure. So here is the Q squared. So I have even a picture. So Q squared here is, when it's small, is the two leptons are close together. I hope you can see this. And then when Q squared is big, they are far apart. And it's only a part of this phase space that you can probe. The rest is full of resonances, so it's much harder to interpret. Right? So you cut, and you only look at the clean part of it, and you measure 2 bins. So this is split into 2 bins. The black are the measurements, and these are different predictions from different groups. It's the ratio is 1 here because in the standard model there's no difference between the couplings to muons and electrons. This is not one because you start to probe the fact that the muon is massive and the electron is much lighter. So if you go to the threshold where you can barely produce the muons, clearly the muons are different from the electrons. So that's the physics behind. So what you see is that this is always away from the standard model prediction. It's about 2 sigma or 2.5 sigma away. It's in the same direction in 3 measurements. So if you were to combine them, the combined significance is more than 4 sigma. It's coming from the same experiment, right? So it's only one collaboration that is able to do this. But there are many more measurements that you can in principle do. All right, so that's where usually people tune out, because that's where, flavor physics becomes very close to chemistry. There are all these transitions, and you have to know what the hell I'm talking about. And so it's all these, these different transitions, and you have to interpret them. But the upshot is the following. So there are many more measurements. They're harder to interpret, and the reason is that you need to know the QCD, quantum chromodynamics. You need to know the form factors. Some of them you can predict reliably. The problem is you're measuring in a regime where the lattice QCD has a tough time. So this has an inherent error of 20–30% that is hard to quantify. But within this 20%, so you see this a big band in the predictions. But even so, there's consistently off. And it's on at the other side. All right? And this is quite a common theme. So now you take everything together. I'm not even going to explain what this is. The only thing I want to note you that this is a P5 prime observable, which tells you immediately it's a horrible thing because there has to be at least 4 of them, and there's a prime. Also, there must also be a non-prime one, right? But there's also a deviation there. No? So it's really, it takes a lot of work. You do a combined fit, and my colleague Wolfgang Altmanshofer and his collaborators did this, and they transformed all this data into these 2 numbers. No? So I said I'll tell you about so this is the C9 and the C10 dimensionless number, Wilson coefficient. It's only the new physics part of it. So the 0, 0 is the standard model. And this is a global picture. So let's say you take only the observables I spent most time on. So this lepton flavor universal observables, where there's no theory error. It's the blue band. You see that the blue bands are already away from 0. This is 1 sigma, 2 sigma, 3 sigma. So as promised, it's about 4 sigma away. You do a global thing where you include everything you think you know about these transitions, with the best guess of theory errors, and you get to this, I don't know, what is this? It should be red, I hope, I don't know, brownish red. It's 1 sigma, 2 sigma, 3 sigma, all right? So this, depending on what you put in, it can be 5 to 7 sigma, but these are now, there's a theory bias in there as well. But it looks like everything is consistent, no? So there could be something there. So the next question is, what kind of new physics could it be? So I just assume for the next 3 slides that it really is new physics. So first question is, what is the scale? So these dimensionless numbers, there were sort of 1-ish, and the scale will be 36 TeV or so. Right? So this 30 TeV. Now, 30 TeV, it's 30,000 times the proton mass. This is high enough that there are going to be 2 types of new physics models that can explain it. They can be grouped in 3 level or loop level. Means the 3 level, if I take h bar to 0, there is still the effect. The loop level, if I take h bar to 0, this new physics effect will completely disappear. Right? So this 3 level and loop level, I'll spend 2 slides on them. So it will be mostly just pictures. So there are 2 distinct types for the ones that are that survive in the h bar to 0 limit. So you can either have a new gauge boson, like a Z prime, so Z with a prime, so like a Z boson, but with a much heavier mass. And then you can have different singlet or triplet, refers to what you do for the lectoweak quantum assignment. So this would take you from a B S quark to muons. What you can also have is a more exotic case where I have a B to muon and then an exchange of a carrier or a mediator, which now has to have both the lepton number, the baryon number has to be also colored. So that's why it's called a leptoquark. It covers both the quarks and the leptons. So it's really a qualitatively different beast than the Z mediator, where there is no color here. You completely annihilate the color, and this is a colorless mediator. So these are the two types, and then of course there are many, many, many references here. The loop level are also sort of three distinct categories. So what you can do is you can do a quantum correction on the quark side, so that's this loop here. So if I take h bar to 0, this thing here disappears. You can do a quantum correction on the muon side, or I can have this box type where everything gets entangled in this quantum correction. Right? So these are the three distinct cases, and of course my favorite one is of course this, for obvious reasons. All right, so that's as far as I wanted to say about B2S mu. So I'll also talk about now, I spend let's say 5 minutes or so on B2 charm, tau nu, so the other set of measurements which are showing anomalies. So the upshot of what I will show you is the following. So it's a relatively different story because it still is very theoretically clean, has a 4 sigma excess, but the effect is much larger. So it's 20% of the standard model, but the standard model is at 3 levels. So this h bar, it survives in the h bar to 0 limit. So that means that the mediators need to be lighter, and then there are many more other measurements where you also probe the same transition. So it's often in conflict with other constraints. So many of the models are excluded, and only a few survive. So I'll first show the experimental situation. So here there are 2 types of transitions being measured. It's always B to C tau nu. It's normalized in the similar way. So I take a transition with a tau lepton, so the heavy guy, and I divide by the same transition where I put in a sum of the electron and a muon. So again, for the same reason, the theory errors will cancel, the experimental errors will cancel, so it will be a much cleaner observable. But then I form also 2 mesons, so it's either a D or a D star. So the charm quark will be in 2 different types of hadronic states. So these are these 2 measurements. So RD is I have a D meson, RD star, I have this D star. But they're, in both cases, they measure the same thing, no? They measure the B to C tau nu transition. The experiment, the global, so the global world average is this, this blob here, the red blob there. There are also some measurements which measure only RD star. There are some measurements which measure both. And there are many more measurements being done. So there are different measurements, really qualitatively different measurements done both by Babar collaboration, Bell collaboration, and LHCb collaboration. They really have very different systematics. There should be no common systematic, or at least there is nothing that people could find. And then there's a standard model prediction which is there. So you see it's about 4 sigma away. These contours, 2 sigma, 4 sigma. What you can ask is how clean is the standard model prediction. So again, our postdoc try to address this is if you try to really push as much as you can the standard model prediction, you see they don't deviate much. And this is quite generous. It's on the errors, you're always very far from the experimental contour. So this seems to be quite robust. From the theory side, nobody knows what could be wrong on the experimental side. I mean, it's really, you see, this has been around for half a decade, and the significance has increased through the years. So it's very interesting. Of course, there's also a problem. The problem is that it's not easy to write models of new physics that would explain this. Doesn't mean that it's wrong, no? Maybe it's just super interesting. So the one that you would first think of is I take a Higgs and I just so I will introduce a cousin of a Higgs boson, let it be charged. This would be the right thing to put in as a mediator. It doesn't work. There are other measurements which exclude this most likely possibility, I would say. Then there's also a W prime, so I take a W boson, it works in the standard model, I just make it heavier and a slightly different couplings. Also doesn't work if you couple to the what's this left-handed currents. So if you have really a standard model neutrino, if you have a sterile neutrino, however it works, it's still viable because why it works is because it's much harder to exclude this with other measurements. Then there's these leptoquarks. So when you take, you can take a big quark, converting it into a tau lepton. So that's the leptoquarks. These are very interesting because you can explain them both of the anomalies simultaneously. If they are vectors, if they have spin 1. So it looks nice before you start writing complete models, and then it becomes very baroque. So nobody really wrote a very nice model that will work so far. All right, so that was about the present status. So now I'll spend the last 5 minutes about the future of these measurements. So there are 2 experiments that are going to take data in the future. One is Bell 2. So that's the upgrade of the B factory in Japan, in Tsukuba, Japan. This will have about 50 times more data. So that's it's the first new accelerator. So it's the first new accelerator after the LHC. It was rebuilt. Also the detector itself was rebuilt, and there was first positron beam was injected in early April. And then 2 days ago, they also saw first collisions. See happy representatives from the collaboration. And these are the first collisions. This would be E plus E minus goes to some hadrons that they see. The other experiment is running, but they're thinking of upgrading the detector. So there are 2 stages of upgrades that they're thinking of. So I stole a plot from what they want to do in this first upgrade. After the second upgrade, they will have 100 times the present data set, and this will translate into quite a striking increase in the precision of these measurements. So let's see, if I take this CKM triangle, that's our CKM triangle, and now what I did is I stripped away all the measurements that go away at h bar equal to 0. So I'm left with only the measurements which stay in the classical limit, so h bar to 0. This would be the standard model measurement. And you go to Bell 2 and you see, I mean, now I have to blow up to even see this very small region, right? So it will be quite striking. And then the question will be whether these quantum corrections sit in the same region or not. So the advancement in these 2 anomalies we'll also see quite a big advancement. This will be coming from both the larger data sets and also the fact that different transitions will be measured. So that's the projection. For instance, this is not even the full, so it's roughly 10 times more data at LHCb that they have now. This would be this black line. And then I found this a slide from Bell, where they also project this, I don't know, it's hard to see, but you see that they're shrinking. No? So this will be, if the central values of the measurements stay, this will quickly become a 5 sigma discovery. So it's really worthwhile keeping an eye on these measurements. The B to S mu mu measurements have a similar story. The measurements will become much more precise. This will be, to a large extent, will be driven by Bell. What I'm showing here is probably one of the most challenging ways of probing this, which is that you look at the completely inclusive measurements. So I don't ask for the hadron states, but you sum over all the hadronic states, which get rid of a lot of the theory error. And even then, if the central value is here, you would have, let's say, a 5 sigma discovery, even from this very hard measurement. If you just do what you were doing right now, it just goes stratospherically into the discovery. Right?
Sorry, I must have missed something. But so you're entering conclusions, but I was just trying to see, does Bell 2 have a forecast when they would actually do or confirm these anomalies? Because I mean, that's really huge. It would be the first signal of new physics.
Yes.
Beyond the Higgs boson.
Yeah. Okay, so there are plots where they show you the, so just as a function of years, how well they do in different measurements at the data taking stage.
Okay.
And then you know how it is sociologically, once you have a 5 sigma,
yep.
There will be a long process where they will look at every possible explanation of where they might be making a mistake,
Yeah.
And we can, if we learn from LHCb, it took them about 2 years to publish the RK star. So there will be 5 sigma, let's say, with 2 years of data, and then God knows how many of scratching your head and making sure that you're not making a mistake. That's, really, when you cross a 5 sigma threshold, I think it's a different game. Because right now, it's a combination of different measurements. It's a global picture. None of these measurements are a discovery. It's just hints.
Yeah.
And the fact that, of course, we know what we're doing. We know from the theory side that we're measuring the same quark level transition. So, of course, I can combine them. But still, it's really a different game when you have a 5 sigma discovery in one channel. Now it's hints. 4 sigma can go away in the combined thing just because maybe there's a systematic that is underappreciated, and when you do a combination, it tends to increase the significance, right? Okay.
No, well, it's really huge.
Yeah.
It's really, really, really huge. Even Sally last week was talking about just how big this is.
Yeah. It's very interesting, but it can all still go away, it's not significant, yeah.
Yeah.
Well, but all right, so I'll conclude. So what was I talking about? So I talked about these 2 quark level transitions. One is a charge current, the other one is a neutral current, showing anomalies. So I'm a theorist, so my job is to defend these lines. So it's clean from the theory side. They're very clean. They are challenging, but they're not impossible to explain both simultaneously. I'm sure now that a lot of attention has been brought to these both anomalies, it's very likely that simpler models will appear, hopefully. And the nice thing is also, I didn't talk about this, but they do imply many new signals, both at this high PT, so high energy measurements like CMS and Atlas at LHC, and also precision flavor. So I talked about LHCb and Bell 2, but then there are also other, so NA62 could see something and so on. All right, thank you.
son decays, could those mechanisms affect some of the non-atomic decays? And would you see?
Yeah.
Yeah.
Okay, I have many backup slides. Maybe I can just explain this. So yes, of course, what you can do is, so I have this BS transition, no? And then let's say I have a Z prime. So instead of having a leptons on the other side, you can just do an SB. So this is B bar, and this goes to an S bar. So this would be BS mixing. And that's like a model-independent strong constraint, which is very strong for this type of Z prime models. I mean, it's really uncomfortable, I would say. But it doesn't exclude the whole parameter space, so it's like cuts in half. It's possible to get around this. No? So what you can do is if you have, so you recognize now the model. So this was the head. This is the quantum correction. There is a Z prime here, right? So that's why I like this model, is because you get rid of this constraint. Because now, if I do the same thing, this is now a quantum correction, or it's a one loop. This would be now a two loop effect, and it's completely negligible. Yeah. So it all depends on the model. But you're right. I mean, and there are quite a few of this type of measurements. And the fact that some models survive is actually quite non-trivial, especially for B2C tau nu. I think maybe, I don't know, at this stage I would say the proper way to interpret this is that it really sort of zooms into particular models, right? And then I would say you write down the minimal model that explains this, so like the most conservative in terms of the flavor structure, and you can still potentially kill or discover this type of models at the LHC, especially if you go to 27 TeV, you would mostly just wipe out all these explanations. Like even if I just like fine-tune the couplings, no? So I mean there is really quite a lot of potential there, but it could also be just a mirage, no? This whole thing.
Along the same line, as a compromise between leptonic decay clean, like mu plus, mu minus, and this one or non-leptonic, is there any analysis of the bottom into strange and tau plus, tau minus? Is it kind of compromise?
Okay, yeah, that's a good question. So you could do B to S tau plus tau minus. So that is, so first of all, theoretically, of course, you would think that it has to be there. It will be enhanced significantly. It's very hard to measure. So the bounds that the LHCb has are very poor. It's tough, no? Because now when tau lepton decays, you have missing ET, no? And in order to see this in the hadronic environment, you need to find the vertex. Now we have two guys that have invisible decays, and it's much harder. Okay. Yeah, that's the problem. Yeah. So it's not. I mean, it looks great, but then experimentally it's too tough. So it would take a while.
But how about the B factory?
Yeah, there it will be better.
Okay.
But I don't know at the top of my head how good they will be. Yeah. But right now it's really not constraining.
Other questions?
I can talk to them later.
Yeah, we'll continue the discussion at the coffee break. I just want to make it from the statistical point of view, in terms of statistics. If you think that these are all physical deviations from the standard one, still the muonic hydrogen is the one with the largest number of standard deviations, right? It's around 5, 6, I think.
Depends who you ask, no? Paul would say that it's a solved problem because he has this Rydberg constant measurement, which is right on top of his muonic hydrogen. Yeah, that's a very, I mean, from new physics side, it's hard, no? As you know. It's very hard to cook up a model that would do it. And from the theory side, it's also not so easy to see what's wrong. You know. And I have no idea. No, you know where I'm pointing the finger at, but
Yeah.
I don't know. I don't know what's. Yeah, it's very intriguing, no?
Yeah. So okay. All right. So let's speak again.